Start with, we have this 555 timer set up as an oscillator to give us a 40 kilohertz signal. The reason we have that is because 40 kilohertz is in the ultrasonic range, and that's the frequency of sound we want to come out of this signal. This generates only our sound. It is not part of the system as a clock or anything. This is our reference signal. It varies from, it goes low for 0.4 milliseconds and high for 3.6 milliseconds. The reason this is chosen is because it takes 1.8 milliseconds to go for a sound signal in normal air to go 2 meters. So we double that so it can bounce back. This signal is inverted so it becomes this and sent to the our NAND gate here. What this will do is only when this pulse is high will it allow an output.
Can you draw the pulses here and then draw the pulses there?
Essentially it's that all the time. Square waves, not triangles, but it's that. Coming into this input will be a signal like this. So that at the output, and sorry, I need to add that next time. Okay. So at the output of the whole circuit, what we end up with is during the time, that 0.4 seconds where this is high, we get the 40 kilohertz signal. And then during the 3.6 milliseconds that it's low, we get nothing. We get a low out. We get nothing. Okay? We then feed this series of of 40 kilohertz pulses to a bandpass filter centered at 40 kilohertz. It has this one that we're using here. It has roughly a band of, if I remember rightly, between 33 and 48 kilohertz. So once it passes through the filter, we end up with a signal like this. We've sent it through the filter because we only want the sinusoidal signal to head towards the main sinusoidal signal to head towards our speaker. The square waves are made up of millions of harmonics of higher frequency signals. We don't want those, we just want the main one. So that's why we put that through the filter. We then take that and amplify it. We amplify it by 20 times here. It's going to clip a little bit for our plus or minus 9 volts. That doesn't matter so much because the majority of it is the main signal. Okay? That is sent to our speaker. We amplify it to the plus minus 9 because we need as much power to send our signal as possible. That will determine how far we can get it to go initially. Okay? That's the transmit signal. Any questions?
Yeah, 9 volts because it's 9 volt battery.
That's right. 9 volts is for the battery power. Right now this thing runs off of 2 9 volts and 3 AA's.
Yeah, makes sense.
Right?
Next part.
Seriously, is there any other questions? Anybody want to go more? Should I go?
Talk about the transmitter's piezoelectric stuff.
Okay. The transmitter here is a 40 kilohertz piezoelectric transducer. What that means is when we put in a voltage, there is a piezoelectric membrane within. You put a voltage in, it will flex one way. You put a negative voltage in, it will flex the other way. The frequency of that flexing will give you the sound, plus the pressure waves that come out of it. That's our sound.
So it's the sound frequency getting converted into voltage.
That's right. If we were to simply put in a plus or plus ground signal, we would have plus flexing it one way, and ground is essentially letting it go. So it would begin to resonate as it goes back and forth until we grab it and push it forward again.
Oh, I see.
Right? That's another reason why we're filtering it and going plus or minus 9 and not just trying to kick it up to the
Otherwise
plus.
it would go like plus 9, come back, and then it could just be doing anything.
That's right. It's plus 9, blah, 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 plus 9, blah, blah, blah.
Yeah.
This way we have absolute control over its position at every point. And there's always going to be some kind of mechanical noise added, but we're minimizing it by doing it like this. Okay? Now we go over to the receiver section. And the one that I actually drew on there.
Yeah. This is the receiver.
Yep, this is the receiver here. We have the receiver connected to an amplifier because, well, the signal we're getting in is very small. It's always going to be. It works in the same way as the transmitter having the piezoelectric membrane, except at this time the pressure waves push on the piezoelectric membrane, which induces a voltage in the membrane proportional to how much it flexed. So that the pressure waves push it back and forth, we get that voltage coming out of the transducer. Okay? We connect that to an op-amp to amplify that small signal. We have this very large resistor here because if we simply connect it to the op-amp, by op-amp theory, the input of op-amp is very high, near infinite. So to the transducer, it looks like the end is flapping in the wind, is completely open. So this wire connect as a antenna for any extraneous noise out there. It's as if it's flapping in the wind. We have no control over it. So if we just leave it like that to the op-amp, we get weird transients going into the op-amp getting amplified by 30 times, which is what our op-amp was doing. Instead, we lock that in down with a resistor to ground so that it essentially drops its full voltage across the resistor, and that's the voltage that the op-amp sees at that point. Okay? The op-amp amplifies it 30 times, goes through a similar bandpass filter that we have on the output, so that we are pulling out any extra sound that we might pick up from the sensor. Even though it is keyed to 40 kilohertz, it can always pick up lower frequencies because that will resonate within. It can always pick up way higher frequencies by harmonic resonance.
Because it doesn't know any better.
Well, the membrane is designed so the optimal frequency it will pick up is 40 kilohertz.
Okay.
But there is always a little bit of extra in there, so we filter out the extra. But every time we filter, we're attenuating a little bit. So we filter and we amplify it.
Just wait, did you just filter it, amplify it, then filter it and amplify it again? Okay.
Because of the R squared, 1 over R squared relationship to power when you're transmitting, what we get back is a lot smaller than what we've sent out. In order to get the distance that we want, we need to amplify the signal a lot. One set of amplification amplifies all the noise and crap that came with it, such that we lose the signal. It drives it directly into saturation. So we've had to break it into these stages where we amplify it 30 times initially because we can, and it's the smallest point, and then we amplify it by 10 times for each additional stage. This is called multistage amplification, and it is very important in this type of circuit so that we minimize the noise.
So amplify 30 times, filter 10 times, filter 10 times.
Okay. Filter.
Okay. Oh.
Now we put that, from all of that, we end up with a pulsed signal that's supposed to look something like that. But because of multiple reflections and everything, what we actually get is the main signal with a little bit that follows after. Okay? First of all, we want to kill the part that goes negative because we're feeding this into digital logic, so we only want positives on this situation. So we use a diode to rectify the system. We don't need all the power that's there, so we halfway rectify it. Right? One diode. This diode, in addition, is also chosen to be too slow to fully respond to all of these changes. So instead of just cutting off the bottom, it also smears together the pulse. So where we start with this multiple, we end up with something that looks like that. Okay? This little peak has given us some troubles because the reflection apparently was very strong at close ranges. So we added this capacitor to smear those two together into one pulse rather than what looked like two to our system.
The capacitor smeared the value of death.
That's right. Capacitor smeared the value of death, if you want to say that. We then fed that into a comparator set for 2 volts, so that when the signal gets to the power of at least 2 volts, fires high, holds high. When it drops below, fires low, holds low. So now we have a existence on existence going for this signal. Okay? We then feed that into a buffer